Hey guys, welcome back to the CS Classroom. Today we're going to cover topic 5, system software. There are two sections. The first one focuses on operating systems and the next one focuses on language translators. And this is basically referring to how code in programming languages is translated into machine code. So when we're talking about operating systems, we're talking about, for example, Windows, Mac, basically the tools you use to interact with your computer in not just a graphical way, but in any meaningful way. Now, a more specific way of describing exactly what operating systems are used for can be found here. So they hide the complexities of the hardware from the user. So for example, if you need to interact with a processor, then there's a lot of code that goes into that particular interaction. And every time you want to execute something on your CPU, you don't want to have to write or execute the code in order to be able to do that. That would just take an absurd amount of time. It'd be super, super difficult for the average user. And this is where the operating system comes into play. You can just click a button and all of that is done for you. For example, let's say that you want to save a file, right? All you need to do is click a button. You don't need to go through all of the technical hoops that would be necessary to conduct that action, right? Next, an operating system provides a platform for software to run on. So as we'll see later, there are a lot of tools that come with an operating system that programmers can use to build software. This means an operating system basically facilitates the use of software and the use of simpler software that doesn't need to dive into all the intricacies of how the computer works, but can instead leave that up to the operating system. So the operating system acts as kind of a support system with a bunch of ready-made tools that developers can use to build software quickly and more easily to run on that given operating system, and generally to run on your computer. And finally, operating systems can provide a user interface. Now, to be clear, there are operating systems that don't come with a user interface. They're just command line based. But the vast majority of operating systems, or really the main operating systems that are used today, for example, Mac OS and Windows, those are mainly as big as they are because they provide an easy to use and efficient user interface that even non-technical users can make use of. We're going to be looking at a series of key tasks: hardware management, memory management, file management, security management, process management, peripheral management, peripherals just being things like computer mice and keyboards, and error checking. Now, I'm going to go through each of these in detail, so I'm not going to cover them too much at this moment. Now, the first key task that an operating system is able to accomplish is hardware management, and it does this by using something called device drivers. And these are basically pieces of software that basically translate signals that come from different components in our computer. So for example, even our processor, our hard drive, basically any of the components in our computer. Here we have GPUs as well, memory, anything that's connected to a USB outlet or port. All of these things send their own separate types of data and signals. And in order to translate these, in order to work with these, in order for users to be able to interact with these and cause some action to occur, we need certain software that translates our user actions into meaningful commands that initiate something in all of these devices. And that's going to be a device driver. This comes with an operating system, and it's basically something that allows us to, for example, click on a button on our computer and then have that cause something to happen in the CPU or the memory, etc. So beyond just allowing this interaction to occur between us and the different components in the computer, also allocates resources like memory and processing power to different hardware components. It monitors their performance to make sure they're doing what they're supposed to within the desired limitations. It manages power usage. And we've already covered handling communication. That's essentially done through a set of tools called device drivers. Now, drivers sounds like it's something that would be unrelated to computers, but this is essentially just a piece of software that allows us to interface with the different components in our computer and have them do something that we want them to do so that we can complete our desired task. So that's how we manage different hardware components in our computer. Now, more specifically, we want to be able to work with memory. And memory management is basically a subset of hardware management because, right, memory is one piece of hardware that we interact with. And basically, the memory management aspect of operating systems, that's going to consist of certain programs or functionality in our operating system that allows RAM to be allocated to any computer program that we open or we use. So for example, if we open Microsoft Word, we want a certain amount of RAM to be allocated so that we can meaningfully work with that program. And memory management software in the operating system does this. It can reclaim unused blocks of RAM, so any any empty RAM, it can basically signify that, okay, this RAM can now be used for other programs. Memory management programs or software will prevent two programs from accessing the same area of RAM so that they're not overwriting each other's information. Also, things like paging, virtual memory, concepts we've talked about before that require us to move data from the RAM to secondary storage. This can also be handled by the memory management programs or software that is part of the operating system. Now, next we have file management. And basically, if you've ever used one of these things before, which you have to have if you ever used a computer, that's going to be part of file management. And the file management software in our operating system, it does a number of things. It divides storage space into units for file allocation. So, for example, if we have a certain amount of storage space, it'll basically turn it into a series of buckets, each of which can correspond to a specific file. We can allocate space to files. So, for example, if we save a Word document, then our file management functionality is going to allocate the required space in our secondary storage to store that document. It's going to maintain directory structures. So, for example, let's say we have a favorites folder. Inside that we have another folder called Amit. And inside that we have another folder called A-Level Computer Science. Those are a series of directories, all within a certain structure that oftentimes looks something like a tree. And the file management software associated with the operating system is going to deal with this, keep it organized, allow us to sort of access files in these different directories. So it's going to specify the format of our files. So there are different structures we can use to store files in a computer system. And the file management functionality is going to specify what that is. They're basically different formats, and they have their own specific way of doing things. File naming conventions, like how we should name files. And then some security functionality, like who can access certain files, whether they're password protected. Finally, and this is probably the most visible example of file management that you would see in an operating system, opening a file, closing a file, deleting a file, copying, creating a new file, moving a file. These are all things that are handled by the file management software in the operating system, or the file management tools that come with our operating system. And they're going to look roughly different. Like there are certain things that are done in a slightly different way, for example, in the Windows operating system and the Mac operating system. But generally, there's not going to be a huge difference in what we as a user see, right? You still have to be able to do these basic tasks. And from what we see, this isn't going to look terribly different between operating systems, but in the background, there are going to be differences for sure. Next, we have security management. We talked a little bit about this. The operating system can be responsible for user authentication. This can be something as simple as just, typing in a password to log into a computer, or putting your thumbprint in. It can control access to certain files. So maybe certain users can access certain files and certain users can't. It can allow us to encrypt certain parts of our computer system. You can log system activity. So anything that a user does can be logged and saved. So you could go back and look at that history to see if, for example, someone did something they weren't supposed to, etc. The security management software in an operating system allows us to detect and respond to security threats. There might be some built-in virus or threat protection software. Things like viruses and antivirus protection, and as well as dealing with system integrity. So making sure that things are saved the way they should be. And so files, just generally the way files are stored is correct, so that that data is not going to be lost. That's all going to be a part of security management in one way or form. This might overlap with other aspects like security management. Certain security management functionality is also part of file management. And system integrity would be part of something called error checking, which we'll talk about later. But by and large, this is all just dealing with securing our information, both from hackers, viruses, etc., and from just system errors that are occurring. Next, we have process management, and this can be super important. So whenever we open a new computer program, that's going to be a process, and that process is going to be dealt with by our processor, and we'll have multiple processors running at the same time, often in tandem, often in parallel, sometimes sequentially. But managing all these processes such that they don't share the same space and memory, and that they're operating in the most efficient way possible requires a lot of code and a lot of software routines. A lot of different tools are working together that are part of process management to make sure these processes aren't interfering with each other, they're not conflicting with each other, and they are operating as efficiently as possible. And also to enable certain multitasking or multiprocessing functionality so we can run processes at the same time. And prioritizing certain processes over others and dealing with interrupts is going to be a process that's handled by these set of tools related to process management as well. Next, we have peripheral management. And this is going to be like, this again is going to kind of overlap hardware management. Again, this is going to deal with device drivers or pieces of software that allow us as a user to interface with devices, with hardware devices. And in this case, when we're talking about peripherals, we're specifically talking about devices that are connected to our computer via something like Bluetooth or USB. And that could be something like a mouse, a webcam, any like sort of external devices that are connected to our computer and allow us to input or output information are going to be handled by the peripheral management functionality of our operating system. This can also deal with buffers and data transfer, and it can deal with allowing us to transmit information between peripherals and our computer in the most efficient way possible. Doing so might also involve interrupts, and again, that's an overlap with process management, right? So, for example, if someone presses Control-Alt-Delete on their keyboard, that's going to be an interrupt. That's going to be interpreted by a device driver and then initiate a window opening up that's going to supersede any other functionality or any other actions that are taking place on our computer. Finally, we have error checking. And error checking basically makes sure that we're saving information. Well, it's not just about saving information or saving data, but basically deals with any unintended results or actions that are happening in our computer. So for example, if we try to do something with their hardware and we have there's an unintended result, so the hardware doesn't function as it should, or software doesn't function as it should, that's where error checking tools are going to come into play. If you've ever seen a blue screen of death, or you've simply had a program shut down unexpectedly, that's part of the error checking functionality in your operating system. So not only is it going to detect and report errors, but it's also going to provide some additional tools for figuring out what went wrong and then recovering from any sort of error that has happened. One other sort of separate, it's not exactly separate, but one other aspect that's a little bit different from these that we've talked about so far in error checking is going to be the ability to back up data. So backing up data basically means copying all the existing data on your computer to a different location. That could be either in the cloud or it could be another hard drive. And this is so that if something happens, something goes wrong with your computer, you can just take your computer's data from that other storage location, really quickly upload it to your computer, so you still have a working version of your computer that you can use. And that can be part of the error checking functionality. Now, that basically covers the different key tasks of an operating system. In addition to the software tools that are used to accomplish those key tasks, we also have other types of software called utility software. And these help users to set up, configure, analyze, optimize, and maintain the computer. Now, again, these are part of the operating system, and these can be found. These are part of the different key tasks that we did look at before, but these are some more specific examples that we need to be able to understand and talk about. Now, the first is going to be defragmentation. We have disk repair, disk formatters, and backup, and I'm going to talk about each of these in more detail. So the first tool we have is defragmentation, and this is slightly complex, but let's get into it. So basically, when you store files, when we're talking about defragmentation, we're mainly talking about our secondary storage or our hard drive, and we're specifically referring to a disk drive, not a solid state drive. And sometimes when you are storing information on a disk drive, the file that you're storing can be broken up into multiple pieces at different locations on a disk. And this is going to lead to a fragmented disk. And this can be problematic because it can just take a longer time to access a file because it's split up in multiple different spots in our hard disk. And it's not going to be as efficient as a defragmented disk where all of the parts of a file are just next to each other. Like if you have to start, for example, like right here at this part and then move over, sorry, it's like kind of hard to find a good color there. If you have to start at this part and then move over to this part right here and then move over to this part right here, it's going to take you longer, particularly if, when the user expects a file to appear as quickly as possible, right? And particularly if we're opening multiple files or many files at the same time, it's not going to be as efficient and it might cause some lag in terms of opening up those files. Versus if you have something like this, you could start here, immediately go to the next contiguous location, and so forth until you've opened up the whole file. So the point is, having your files split up between different locations on your hard drive is much less efficient than having them all in the same contiguous location where like all the different pieces of the file are right next to each other. Moreover, this head right here, so this little device right here, needs to move less. It needs to move less distance, or a smaller distance, I guess, less quickly, really. Because instead of having to jump from here to here to here to here, it can just start right here and then gradually move that way. So basically having a defragmented disk, which is what this is, where all the pieces of a file are next to each other, can also reduce the amount of wear and tear on your hard drive and make it last longer. So we use software to make sure that this happens, and this defragmentation software is continually making sure that our files are stored next to each other. Moreover, it's making sure that free space, that where nothing is stored, is also next to each other in contiguous blocks. And the result is that we're reducing the time it takes to access files, we're letting our hard drive last longer, and we're also freeing up space, like right here, which allows us to find somewhere to store our files more quickly. The next piece of utility software we're going to talk about is going to be disk repair software. And this is another piece of software that's going to be, it's going to be something that we can use, but also it's going to be something that's going to be operating in the background. And this piece of software is going to look for bad sectors in our hard drive or logical errors. So anywhere where files are different pieces of files are not connected the way they should, or their connections in our file system doesn't reflect the correct way that they're related to each other, that's going to be something that the disk repair software is going to try to fix. And this is going to make sure that all files are accessible to us any time, and they're not corrupted, meaning there aren't errors that either lead to data loss or just prevent us from opening up that file and accessing that data. And if it's just, for example, like a music file, it's not a big problem. But if files that are essential to the operation of the operating system are not correctly linked to each other or can't be accessed, this can lead to real system stability issues that can prevent us from working with our computer. And the disk repair software plays a role in preventing that. Next, we have disk formatter software, and we kind of touched on this earlier, but basically different operating systems set up or organize their files in different ways. And these different ways are referred to as file formats. They can look something like this: NTFS, FAT32, X34, X4, etc. And disk formatter software helps us to format new disk drives or new drives that we hook up to our computer so that they can be used by our operating system and by any other computer that has the same operating system. They can also erase existing data on a disk, making it ready for new data storage. If we need to actually just use that piece of hardware in order to boot up another operating system and install it in our computer, a disk formatter can help us format it in that way as well. Now, I'm not saying this is something that happens very often, but it is another useful aspect of a disk formatter. And generally, the idea behind a disk formatter is it makes sure that whatever storage drive we hook up to our computer is formatted correctly so that we can store data on it without any errors. And this formatting can just allow for compatibility with different computers, but it can also allow our files to be accessed more efficiently by virtue of give a particular file system format and improve disk performance based on how those files are organized. So this allows us to basically store stuff on other drives. So for example, if you hook up a new USB drive, we want to install a new hard drive in our computer, a disk formatter can help with that. It can erase the existing data on the disk and then format it according to one of these file formats that allow us to utilize a file system that allows us to basically access data as efficiently as possible. Finally, we have something called backup software, and we kind of referred to this earlier. But backup software basically allows us to either copy certain files in our computer or the entire system to other locations like an external drive or cloud storage. And we'll often do this copying, like for example, every week or every day, basically at regular intervals, so that whatever is at that other location reflects the current state of our computer. And this is so that if we have some sort of if you have a virus in our computer, or we just have some error that happens in our computer that doesn't allow us to access our data, we could just take that data and we could copy it to a new computer, like a new hard drive, another computer, or overwrite our existing data or the existing data on our computer to allow us to at least have a working version of our operating system and access our files. So basically protects against data loss because we always have a copy of the most recently, of basically the current state of our computer somewhere else that we can access if something goes wrong with our computer. Now that's kind of it for utility software. We're going to cover some other sort of random concepts involving operating systems. And the first is something called program libraries. Now, this is kind of like a weird, this can be difficult to understand. So what I want to do first is look at an example of a program library, and that can be the Windows API. Now, program libraries are generally used by programmers when they're creating software for a specific operating system. And so a great example is the Windows API, which is a set of software tools that would allow programmers to create programs for Windows specifically. Now, these are libraries, so they're like little, I guess they're little packages of code that we could include in our software programs. If you've done any programming and you've done, like for example in C++, you used include, or just in Python, you imported a library, for example, to generate random numbers, or to, I don't know, to when you're building web applications, this concept is familiar to you. But basically in our program, it would give us some functions like create window or read file or write file that allow us to do these things specifically in a Windows operating system. So that means program libraries, they generally consist of blocks of code that any programmer can use in their program to write programs for a specific operating system that are specific to that operating system. So like the Mac operating system would have its own set of libraries as well that could be used by programmers to create software for that particular operating system, and Linux would have the same as well. Now, to give a more like formal definition of what these are, they're basically precompiled routines, functions, and resources that can be used by programmers to create software programs. They're reusable, so you can take one of these blocks of code, use it in one program, and then use it in another program. And it basically saves a lot of time because you have ready-made tools that you can use to integrate your software and allow it to seamlessly work with a given operating system. Now, if we're looking at this particular chart right here, we have computer hardware, we have our operating system that interfaces with our computer hardware, and then we have library routines, which can also be referred to as program libraries, that basically interface between our programs and the operating system. So these are generally going to be used in code by programmers to create programs that can effectively and seamlessly talk to our operating system. Now, there are some benefits to this. The first is reusability. We can use the same library, the same group of code or block of code, not block of code, I'd say like, I guess the same code or the same file, which I'll refer to as a library from now on in different programs. Oftentimes these libraries have been continually developed and have been refined so that they can execute a particular functionality in the most efficient way possible. So for example, if we have a library, we have the Windows API, which is a program library. That code has been refined so that it allows us to open a window or create a window in the most like efficient way possible, using the least amount of processing power and memory necessary. It's modular, so we'll have different libraries, and each of them will have a very specific functionality. And we can basically use multiple libraries in the same program, and they're not really going to overlap with each other. And finally, they're standardized. So if you basically create a program using a program library, it's going to look the same on any computer that has the same operating system. Now, next we have something called DDLs, and these are similar programming libraries. They have a specific functionality, which I'm going to again talk about using an example. So like DDLs are often used, if we're just talking about a very specific example in the context of Windows, DDLs are used in Microsoft Office programs. And things like spell check, working with XML. I guess spell check is probably what you're most familiar with. That's an example of a DDL. And one aspect of DDLs is they can be used by multiple different programs. So you can use spell check in Word, in Outlook, even in PowerPoint. And so it's kind of like a plug and play. It's kind of like a plugin that can be used across different programs. And this plugin, like I guess spell check comes included, but oftentimes in Windows programs, you can install additional plugins that may not have come like already installed with your software. And those can give you additional functionality. So for example, if you're doing a lot of finance stuff in Excel, you could find a finance plugin online, download it, and add it to Excel. And this is usually going to be a DDL. And DDLs are going to be very efficient tools for a specific purpose. So you might be able to do like financial stuff on your own without a DDL, without this like plugin or add-in, but this plugin is going to be optimized so that you can do those things as efficiently as possible. Again, I think the best way to envision DDLs is like as plugins or like additional pieces of software or code that you can install in an existing program to enhance the functionality of that program. And so if you go back to the more formal definition, these are files that contain reusable code and data that can be used by multiple programs at the same time. They allow programs to share functionality without embedding the code directly. So that's kind of going back to this sort of like plugin paradigm, where with DDLs, these are sort of like standalone pieces of code. So they're separate from the programs we're using them with. So for example, the spell check functionality, the code that makes up that functionality, is separate from Microsoft Word, Excel, etc. But we can use that functionality from all those programs at the same time in an efficient way. And one other significant aspect of DDLs is that they provide dynamic linking, meaning they're loaded into memory only when needed. So for example, if we download a finance plugin for Excel, we may download that, and that may be installed in Excel, but only when we need to use that functionality is that going to be put into memory, which allows for greater efficiency, because if we're not using it, then we only need to use the memory required for Excel and not that additional plugin as well. Same thing with something like spell check, which actually may come installed in Microsoft Word. That's still a DDL, and only when we click that spell check button are we going to take the code that makes up that functionality and load that into memory, which means that if we're not, then we're not using as much. If we're not using spell check, then we're not using as much memory as if spell check was not a DDL, and things are just going to be more efficient. Overall, it's going to reduce the big advantage of DDLs. They reduce memory usage. That kind of brings us to our benefits: reducing memory requirements for programs, reducing file sizes, because, for example, spell check is not necessarily going to be part of Microsoft Word. So if we just include the core Microsoft Word or install the core Microsoft Word, then it's going to be a smaller file. Maintenance is easier. DLLs are like smaller modular components separate from the main program. So for example, if we wanted to update the spell check functionality, or we wanted to update that finance plugin, we don't need to modify Excel or Word as a whole. We can just modify those specific plugins, let the user know they need to re-download them, or allow for an automatic download, and we're good to go. That really simplifies maintenance or upgrades of different pieces of functionality in a program. And part of that is we don't need to recompile the main program. We don't really need to do anything with the main program when we update DLLs. And these all encompass that, right? So we can make changes to DLL code that adds additional functionality to other programs, like for example, Word or Excel, without having to change the code in Word and Excel. We only need to change the code in that DLL. And I've been talking a lot about Word and Excel because those are programs you're familiar with, but there are a lot of other programs that make use of DLLs, not just those particular programs. And I realized that actually I messed up DDL and DLL. Sorry about that. This should be DLL, dynamic link libraries. So if you see DLL anywhere, that's what it means. Again, apologies for the mix-up. I just realized that after going through all these slides. Now, before we move on, I want to take a look at an A-level question that addresses a topic that we haven't covered so far, but that overlaps with other topics involving hardware, and this is interrupts. So to clarify, an interrupt is basically an action that prevents or stops a processor from executing its current instruction or executing its current action, and instead prioritizes a different action that's when that initiated the interrupt. Oftentimes, this is used to handle emergency or higher priority situations that need to be handled immediately. So the operating system is responsible for basically passing those interrupts on and handling interrupts that occur that can be initiated either by software or either by hardware or by software. And we're just going to look at a question that forces us to distinguish which one is going to be used. So first, buffer full. So a buffer is going to be, this can be a variety of things, but usually involves something involving files. So I'm going to say it's a software interrupt. Printer out of paper should be a hardware interrupt. User has pressed a key on the keyboard should be a hardware interrupt. Division by zero should be a software interrupt. Power failure should be a hardware interrupt. And stack overflow should be a software interrupt. Now, a stack overflow is basically a type of error that can occur in a software program. Hence, it's going to be a software interrupt. Let's see if we got those right. Let's see. Okay, so yeah, I think we're good to go. The main distinguishing factor is whether this involves hardware or software. So it's actually pretty simple, but I still wanted to kind of go over it just so you have an idea of how to deal with an issue like this, or rather an exercise like this. That being said, let's move on to the next section in this particular topic, which is language translators. Now, with language translators, we're talking about how to take programming languages or code written in programming languages and translate those into machine code that can be executed on a CPU. So essentially, we want to go from a source file with our code to machine code. And there are a few ways to do that, a compiler being one of those. So compilers are usually used when a high-level language program is complete. So we've written the entirety of the program. They take all of the code in that program and then translate it to machine code. And when they do that, they also create an executable file. And if you've ever seen a file that ends with .exe, particularly in the Windows operating system, then that's going to be an executable program, and this can be run without the source code. So basically taking the source code with all of our code, this particular file is going to consist of code written in C++. We're going to compile it, which is going to turn it into machine code. And that compiled code is going to be in the form of an executable file. Right here we see .exe, and we can just go ahead and basically click on this, execute it, and it will do whatever we've specified in our source file. Now there's some important differences between compilers and interpreters. So obviously interpreters translate and execute code line by line, versus the compiler translates the entire code into an executable code file, and then we execute that when we want. So in general, because we are going line by line, we're conducting both the compilation and execution line by line. Interpreters are going to be much slower. With the compiler, we're turning everything to machine code. We're going through that whole machine code process first, and then when the user wants to execute the program, then we're going to do the execution. So essentially, right here with compilation, when we're doing the compilation, we're devoting time to that compilation, and the user may not even see that, right? Because oftentimes the user is just going to receive the executable machine code file. And then the time that the user needs to wait is just going to be while that file is being executed. So if we talk about it really simply, the user is never really going to experience this translation part unless they're the programmer. They're really only going to see the execution part, and so it's going to seem like it's a lot faster for the user. Next, compilers are often so when we use compilers, we're often taking code and compiling it to work on a specific operating system or platform. So we're going to need different compilers for different operating systems. Versus with interpreters, for example, Python is an interpreted language. We can use these on any platform. We just need to make sure we have that interpreter installed, and that interpreter will have the tools necessary to, first also that interpreter is using a virtual machine, right, for execution. And a virtual machine is like a kind of made up abstract computer within the computer. And that virtual machine is going to allow us to run code on any platform, because the code is running in the virtual machine. We're not really depending on the operating system to be able to execute that code. The operating system is going to show us the result of that execution. So the point of this is that we can use an interpreter on any operating system. A compiler needs to be there needs to be a different compiler for the same programming language for each operating system. And because of this, because interpreters are sort of platform or operating system agnostic and compilers aren't, oftentimes compilers are going to be more optimized to run as efficiently as possible, to create programs that run as efficiently as possible on a CPU, and interpreters are going to be less optimized for that because they use this virtual machine to execute the code. The operating system lets us see the result, and we're not really generating code specific to a given CPU or operating system. Now there's a few other things, like error handling is a big one. This says errors can be corrected in real time, one at a time. What this basically means is that we're going to be dealing with errors line by line, and we're going to fix it. Like if our program runs into an error and stops, we're going to stop running that program, go back, fix the error, and move on. Versus with compilers, we are going to see all of the errors at once, right? Because we're going to compile the code. There are going to be certain errors that are found at compile time when we're compiling, and at runtime when we're running the program. But we can only deal with those basically after we've compiled the code and we're executing the program, and we're going to see all of those errors at once, either at compilation or execution. So I wouldn't necessarily say error handling is necessarily easier with interpreters, but when and how those errors are thrown and how we deal with those can be different between both of them. Like we're mainly going to be dealing with errors in programs that have been compiled after the entirety of the program is complete and we're executing that program, versus with an interpreter during development. Because it's executed line by line, it can be easier to find and deal with programs while we're just developing that program. And oftentimes this is why Python can be viewed as an easier language for beginners. Now, another paradigm we have is when compilers and interpreters are working together. So generally how this is going to work, and actually to be fair, like this is how interpreters in general work. So the idea of compilers and interpreters working together is not something separate. It's actually just how interpreters work. We just don't really talk about the compilation that much. So if we have an interpreter, then we're going to have an initial compilation step that converts source code not into machine code, but another more optimized form called bytecode. This bytecode can be interpreted by something called a virtual machine. And at this point, we'll also take in inputs, like if we want the user to type in some information. And that virtual machine is going to handle the actual execution independent of the operating system. Remember, the virtual machine is like sort of a ghost computer, like a made-up computer that basically pretends to be a computer but is not an actual physical computer. And in our operating system, so like on our computer, we basically see the output of this virtual machine on our screen, with the virtual machine doing the actual execution. Now, partly because we do have this like separate imaginary computer doing the execution, we are going to have more overhead, meaning we're going to require more processing power for interpretation. But we already kind of touched on that when we talked about both optimization and slower execution for interpreters. So really, like, the idea of compilers and interpreters work together is really just at the core of interpreters. But I wanted to highlight that in this particular slide to make sure you understand this is what is happening. So that brings us to a good A-level question. State one reason why some high-level languages are partially compiled and partially interpreted. And a good reason can be to work on different platforms, because we have the virtual machine doing the execution instead of depending on the operating system, the native operating system, to do the execution. And actually, I think honestly, that's like the biggest reason. There are some other reasons here. Code is optimized for the CPU as machine code. To be honest, like these, they don't make as much sense to me. It says source code does not need recompiling, so more efficient to run. I don't know. I think those reasons are kind of more difficult to wrap your head around. I think this is probably going to be the main one you'd want to go for. Partially compiled programs can be used on different platforms due to interpretation. Now, we can both use compilers and interpreters in order to translate our code into machine code and really just generally engage our development process. So as we talked about, for example, Python is a language that's largely interpreted. But the thing is, we don't have to just interpret Python code. We can also just directly compile Python code if we want to. So if we're developing software with both compilers and interpreters, here's what the workflow would look like. We'd use an interpreter while writing the program so that we could test and debug line by line. So as soon as we write a line of code, we can go ahead and test it, see if it works. If it does, move on. If it doesn't, fix it, and then continue writing code. So an interpreter can be super useful in the development process, but it can be slower to use an interpreter for a user to execute a Python program using an interpreter as opposed to a Python program that has been already compiled to an executable file. So once we've used the interpreter to go ahead and run code line by line and then refine and fix any errors that we have, once we have that code that we know works without errors, instead of just sending a .py file, for example, to the user, to an end user who is not technical to run, we can actually just compile our Python code into an executable file like a .exe that user can directly run, and that'll be faster than if the program was interpreted, and also just easier to use because all the user needs to do is just click on the .exe and just run it. So that's how we can both use interpreters and compilers in our workflow. We can use interpreters when we're doing the actual development, and then when we want the user to be able to execute a program, we can use a compiler. Now, the next way we can translate code to machine code is using an assembler. But this is a very special case. Assemblers are only used with assembly language. Assembly language tends to be code that is not that does not correspond to a high-level programming language like Python or C++ or whatever. It's usually very low-level, and it's something that is more difficult to write. You need to specify different actions, like, so for example, loops or even arithmetic operations in more lines of code. Also, this code tends to be specific to a given processor or a chip in which we're executing our code. And assemblers are basically going to take this assembly language and turn it into machine code, which can be executed by the processor. So this is something that needs to be known. In other topics, we actually look more closely at assembly language and how that process takes place. But for this topic, you just need to know that that exists. An assembler exists to take assembly language and turn it into machine code. Now, finally, we're going to look at something called an IDE, which is an integrated development environment. If you've done any coding, you've probably used an IDE, like VS Code. I mean, there's a lot like VS Code or like PyCharm. There are a lot of different IDEs out there, and these are software programs that are specifically made for you to be able to write code as efficiently as possible. And when using IDEs, there are 5 capabilities you need to know for the A-level exam that I'm pretty sure all IDEs can offer you. The first is a breakpoint, and the breakpoint allows you to stop code at a specific point and in your code. So maybe you execute the first 3 lines of your code, and then if you put a breakpoint at line 4, you can see what values all the variables in that code hold at that particular point in time. It's essentially like freezing your program at a given point in time. And what this allows you to do is see what each variable looks like, what value it holds, to try to trace any bugs that exist. Next, we have dynamic syntax checks. And these will basically, if you've ever used an IDE, when you're writing some code that's incorrect, you may see a red line underneath it because it doesn't follow the rules of a given computer program. That's going to be an example of dynamic syntax checks. As you're writing code, it's going to indicate when there are errors in your code. Next, we have context-sensitive prompts. And this doesn't exist in all IDEs, but in most modern IDEs. And this is basically like if you're writing print, or if you're writing a pretty well-known line of code or set of commands. This will basically automatically suggest what the next word or what the next term in your line of code should be. Next, you have single stepping. This is kind of similar to breakpoints, but this allows you to run your code line by line, and so that you can see the values of your variables in each line of code. And again, this can be used to sort of see if there are any errors. With breakpoints, you're just stopping the code at a specific line. With single stepping, you're just going through line by line and seeing what the values in your program are holding. Finally, we have collapse and expand code blocks. And this is purely like cosmetic. And this allows you, like if you have large amounts of code, this can allow you to close certain blocks of code so you can focus on other blocks. And you may already be done with a given block of code. So for example, if you have void setup and you have code in here, you could collapse it so you just see void setup and you don't see any of the code here, even though it's still there. And this allows you to focus on a specific block of code without being distracted by other groups of code. So this isn't really going to make any changes to your code, but it's just what is visible at a given amount of time, or at a given point in time. There are also going to be some more obvious visual features of IDEs. We already cover expanding and collapsing code blocks, but we can also have auto indentation and formatting. So this is going to indent, particularly with Python IDEs. Or it's going to make sure it's going to format your code in a certain way so it's easier to read. Again, this is very cosmetic. Also, you might have pretty print, which turns different parts of your code certain colors. So for example, an import statement is going to be orange, input might be purple, any loop related commands might be orange. It's basically it's going to format code, but also with pretty print, it's going to color it so that it's very easy to see what's going on. Anyways, that brings us to the end of this particular topic. And I want to finish this video off with some channel updates. So as you know, I've been going pretty slow, partly because I started a new job and I just don't have enough time to make these videos. But I'm going to continue working through paper 1. Also, I was going to create a paper 2 course, but I'm planning on releasing paper 2 material topic by topic. So paper 2 is basically topics 9 through 12. And I'm going to start with 9.1, 9.2, 10.1, etc. Release them at a more slow pace rather than all together. But that's because that's all I can really manage right now. If I were to just wait and release all the paper 2 material at once, it'd probably take me a couple of months. Versus here, I can kind of drip feed this material as I'm making it. Anyways, if you enjoyed this video and found value in it and would like to see more like it, please remember to like this video and subscribe to the channel. I'll see you in the next video.